This is part D of the gas laws. Notes, this video will discuss Gay-Lussac's law and the temperature and pressure relationship. So Gay-Lussac's law, there is a directly proportional relationship between pressure and temperature when volume and amount of gas are kept constant. And so this is really similar to the last gas law we looked at with volume and temperature. And so that formula looks the same. So if we have a low temperature, then or if our temperature goes down, our pressure is also going to go down. And that is to kind of maintain those when we have that same volume and that same amount of gas. And then if we have a high temperature, that's going to be a high pressure. If we look at this here, notice both of these have the same volume because they're the same size. We have the same number of molecules with the same dots. But if we have a low temperature, those are not moving as quickly, we're going to have less collisions. As the temperature rises, those are going to move more quickly. There are going to be more collisions with our container. The equation P1 over T1 equals P2 over T2 is how we can look at this relationship algebraically. So let's look at our first example. A gas with a pressure of 100 times 10 to the third kilopascals, so it's a pressure, at 20 degrees Celsius is heated until its temperature is 50 degrees Celsius. What is the new pressure of the sample? Assume volume remains constant, and then we're going to also sketch a model of this situation. So as we're looking at those, we have kind of those two time frames. We've got our temperature, and I said volume here, but that is a temperature 1, and then we also are going to have a second pressure and a second temperature after that has changed. So pressure 1, 1.00 times 10 to the third kilopascals. We've got 20 degrees Celsius. Well, we need to add 273 to get that temperature in Kelvin, so 293 Kelvin. We do not know what the pressure is. That's what we're looking for. And the temperature after is 50 degrees Celsius, so plus 273. We get a temperature of 323 Kelvin. Going and plugging that into our formula, I've got 1.00 times 10 to the third kPa all over that 293 K. That's going to equal P2 over that 323 Kelvin. Solving this one again, if you prefer to just divide this and then multiply that 323 over, that's great. We can also just show this times 323 Kelvin on both sides. Notice that our Kelvin units cancel, leaving us with that unit of kPa. And so P2 equals, we get, I get 1,102.38. Looking at our sig figs, we have 3 sig figs, 3 sig figs, 3 sig figs. And so as we're looking at this, if we round, we need to round to the nearest whole. But without a decimal, it's 2 sig figs. With a decimal, it's 4 sig figs. So let's go ahead and write that in scientific notation. 1, 2, 3, 1.10 for that third sig fig times 10 to the third kPa is that pressure after the change in temperature. This one asks us to do a model. So as we are looking at this, we're going to kind of have that before and after. And let's take a look at our variables too. We had that change in pressure. Our pressure after the fact was 1.10 times 10 cubed kPa. So that pressure went up, which means in our picture, we're going to want to see more collisions after the fact. And looking at our temperatures, we could have predicted that because we have 293 up to 323. When the temperature goes up, the pressure will do the same thing because of that direct relationship. So before, we're going to assume the volume remains constant. So whatever volume I choose before, I'm going to do the same after. We also are going to have the same amount of moles. And so if I choose, and again, I choose like 4 to 5 dots, just enough so I can represent what I need to, but not too many that I feel like I'm drawing a million moles. And then with that, we're going to show our pressure going up after. And so when I look at these, my temperature is going to start lower. So I'm going to make the length of those a little bit lower. And I also know my pressure needs to go up, so I'm not going to have as many collisions at the start. And so maybe I do just 2 collisions here. So my collisions, again, the molecules that are hitting our container. So this one has 2 collisions. And now as we show that temperature go up, my arrows have to get longer, meaning that those molecules are going to run into the container or each other more frequently with that. And we can show those bouncing off the container. I have those longer arrows showing that temperature increase. And now with those 4 collisions, that shows that our pressure is greater. Example 2. A sample of gas has a pressure of 37.5 kPa at 50 degrees Celsius. What is the new temperature at standard pressure? Assume volume remains constant. So kPa is a pressure, degrees Celsius is a temperature. What is the new temperature? We're looking for a temperature at standard pressure. Well, we know what standard pressure is. Remember STP, that tells us standard temperature and pressure. And so that will tell us standard temperature is 273 K. Standard pressure is 101.3 kPa. So those, if are ever referenced, then we can use those. So we've got a pressure one and a temperature one. Those just have to be conditions that are happening at the same time. So that's going to be my 37.5 kPa and my 50 degrees Celsius. But we need to convert that to Kelvin by adding that 273. And so we get 323 Kelvin as T1. Pressure 2 is standard pressure, so that's 101.3 kPa. And temperature 2 is what we are looking for. And so as we consider these, well, my pressure is going up, and so I should expect my temperature to do the same. Those are directly proportional, and so what one does, the other is going to do as well. So as I look at plugging these in, 37.5 kPa over my 323 Kelvin equals that 101.3 kPa over T2, which is what we're looking for. And we can cross multiply. So we get that 37.5 kPa times T2 equals 323K times 101.3 kPa. And then to get T2 by itself, we're going to divide both sides by that 37.5 kPa. If you prefer to algebraically do these in a way that makes more sense for your brain, that's great. We just want to make sure we're getting the same answer. I'm going to go ahead and plug that into my calculator. And I got 872.5, and then that is Kelvin. Let's look at our sig figs. 323 is 3 sig figs, 4 sig figs, 3 sig figs. So I'm going to, that 5 is going to round this up. 873 Kelvin is T2. If we were asked to find what that temperature was in degrees Celsius, well, we would have to take that 873 Kelvin and we just subtract off that 273 in order to get what the degrees Celsius would be on that. So that would be 600 K. You need a decimal. Oh, no, 600 degrees Celsius. We would need a decimal to maintain those sig figs, and that is what the temperature would be in degrees Celsius. That is the end of this notes video. Part E will continue in the next video.